I will be doing a discussion of designing and building deterministic high-frequency trading systems. The fundamental thing about this talk is how to make components do, or microservices do, little as possible. The less your microservice does, the faster it will go. So a little background about me. I have the most answers in the world for Java and the JVM on Stack Overflow, about 13,000. I'm a Java champion. Most of our clients are tier 1 banks, US and UK based. Last year we had over 17 million downloads of our open source software. And we're a self-funded company and with revenues of around 2 million a year. Last year we built an OMS, a fixed-based OMS, which had 3 microservices, and the end-to-end latency from wire to wire. That's from a message being on the network to a response being on the network again, through 3 microservices. That's making 6 persisted messages in this end-to-end process. We achieved a worst 1 in 1,000. That's the 99.9 percentile. The worst 1 in 1,000 latencies were under 20 microseconds. So it's a 50th of a millisecond was the worst 1 in 1,000 latency. So that's the sort of target we're trying to achieve with these series of microservices. And in fact, if we're just persisting messages passed between 2 processes, we can do that in under a microsecond pretty consistently. So worst 1 in 100 being under a microsecond. And that's to write a message, persist it, and then read it in another process, and then deserialize it. So that's the sort of target. We get better results on the typical, but it depends on your situation. So obviously, a very short, simple message is quicker. We've got benchmarks of down to 0.1 microseconds. Also, we have low latency replication, and often that's key in for redundant systems, or if you want to have confidence that you won't lose any data. And at the moment, that adds up to about 30 microseconds on top of whatever your network round trip is. A couple of years ago, we replaced the core FX trading system of a bank, a tier 2 bank, and they saw an ROI for the entire project, return on investment in just 3 months. So that the entire cost of the project, they saved, they made more money as a result of replacing their system, and the amount that they made in 3 months, was paid for the entire project. So we focus very much on, for low latency, we focus very much on individual processes on a shared machine. So you've got one big server, or redundant big server, and we tried to make it that those processes can communicate as fast as possible. The reality is that you often need to deploy it onto something like Alibaba or AWS, and then it's across multiple machines. But we tried to make it that the overhead is that our software adds is as little as possible. And then how you choose to deploy it is entirely up to you. But for the best results, running everything on a single machine, it will give you the lowest possible latencies. Another thing that's unusual about low latency systems is that to get consistent latencies, you want to have very low utilization. So you want to design your system such that it's only ideally about 1% busy at any one time. The reason you need it to be about 1% busy is that 1% of the time, instead of having a queue of 1 order, you will have a queue of 2, because 1% of the time it will be waiting. It will still be processing the previous order when a new one comes in. So if 1% of the time you have 2 orders in your queue instead of 1, you've essentially doubled your worst 1 in 100 latency straight away, just because you're 1% utilized. If you're 10% utilized, you're increasing your worst 1 in 100 dramatically because you now have queuing. Essentially, when you're designing a system for your worst 1 in 100 case or your worst 1 in 1,000 case, you're designing a system where everything goes wrong at once in terms of performance. Every delay in the system is happening at once. So you can't rely so much on caching, for example. Caching works well most of the time. That's what it's designed for. Most of the time, it has the information you need. Maybe a cache might work 90% of the time, and that would be a good cache. However, if you're worrying about the worst 1 in 100, your cache never works. So you're actually caches that don't work, and the times when they don't work are actually slower. So caches don't easily solve these kind of problems. So where are the sources of latency in your system? So when you design a low latency trading system, you want to know every piece of latency in the chain. So I've worked at places where they measure how long the network cable is between their server and the exchange. And in fact, the exchanges make sure that no matter how far away the server is, the length of cable is the same for everyone, just to ensure fairness. 100-meter cable adds a round trip of 1 microsecond. So the length of cable, even down to the length of cable you're using, can make a difference. So you want to know where every piece of latency comes from, because they all add up. It's like a chain. So one of the areas to focus on is the latency introduced by your operating system or your network card. So it's quite common in the lowest latency systems to use what's called kernel bypass. So it doesn't even go through the operating system. You need to look at how is your messaging distributed, because that in itself can add dramatic latencies. So for example, in Kafka, they get latencies of around a couple of milliseconds. We aim to have latencies 1,000th as long as Kafka. So just in the choice of software, you can get a dramatic difference in the amount of latency introduced. Your core business logic, how does your business logic work? So one of the key differences in low latency systems is that you don't want to be going off to any external resource to do your processing. It's not appropriate for a low latency system to be querying a database or updating a database, because that is now introducing an extra dependency that is not only difficult to test, but difficult to ensure you get consistent latencies. A typical database request can be anywhere up to a millisecond. And if your ambition is to have a sub-millisecond microservice completely end-to-end, consistently, then you don't actually have time to do any database requests. Another thing to watch out for is garbage collection. So creating garbage has 2 problems. The most obvious problem is when the GC collection occurs, you pause your JVM. So that's the most obvious problem that people see. And that can be a problem in any Java application that you use. However, not only is it causing a problem when you run out of memory and it has to collect, but it is actually causing a problem every time you create a new object. Because when you create new objects, you're actually filling up your CPU cache with garbage, quite literally. And that memory pressure pushes out the useful data, and now means that every memory access is more expensive. So you want to reduce the amount of churn, reduce the amount of objects that you're creating and pushing out, even if you're not worried about GC cost. So we design our systems to produce some objects, but as little as possible. So emphasizing the point, the less work you do, the faster your application will be. And you can realistically reduce what a microservice does down to microseconds if you just focus on only what needs to be done and nothing more. So I've got a little example here. So this is a benchmark written in JMH. JMH is a good, robust tool for measuring the speed of code. So I'm doing the same operation 2 different ways with JMH. So one common way of doing mathematics in Java is to use big decimal. So big decimal works well in the sense that it ensures that you never see any representation errors like you do with double. The problem with big decimal is it will always look correct, even if it's not. Whereas double, if it's not quite correct, you didn't round it correctly, you will see that there's an error and you can fix it quite quickly. But with big decimal, if you have a rounding error, you just won't know. It's not obvious unless you know what the answer should have been. Another problem with big decimal, particularly in Java, unlike C#, is it has no language support. So the code for big decimal is cumbersome and a bit more error prone. If you're using C#, for example, decimal has this nice support within the language, and so you're less likely to make errors. So how did these two perform? Well, the average time to do this operation using double is about a 20th of a microsecond. But using big decimal is around 5 times higher to do the same thing. However, if you start to look at the outliers, you start to see how much difference it makes. The worst one in 1,000 is now already about 20 times worse to do the same thing. And more importantly, the worst one in 1,000 is getting close to the 20 microseconds you might like your microservice to take. So if one simple maths operation is already using your entire budget for how long you want your operation to take, you've got a real problem using this approach. So even though we target very low GC and very low amounts of garbage, doesn't mean that we don't ever GC or we don't ever create garbage. Because the reality is that it becomes increasingly difficult to write code that never creates garbage. It gets more and more complicated. And that effort isn't really merited. In terms of maintainability, it is worth optimizing your code, but only up to a point. So the sweet spot where we generally say it's not worth optimizing any further is when you're producing less than about 1 gigabyte an hour of garbage. So at about 1 gigabyte an hour, you can create an Eden space of 24 gig, and you can literally run for an entire day with no minor collections. I did this first built a system like this about 8 years ago. And because I was also watching the system running, I could actually chart how much the Eden space filled up over the day and watch it. And then essentially at a fixed time every day at 5 a.m., it would do a single GC at a planned time when we weren't trading, and then it would just continue from where it was up to. And then slowly the Eden space would fill up about half in a normal day and more than half on a busy day. So it is possible to build systems where the amount of garbage you're producing is very low, so low that it doesn't matter, but you don't have to resort to never creating any garbage. That's an extreme that's probably not merited. I have worked with systems where they aim to produce no garbage at all, but in general, the code is so cumbersome and it's so difficult to write code that way that, in my opinion, it's just not worth it. So this is something I mentioned yesterday. Well, I'll go over it very briefly again. So one of the things we advocate for building our microservices to be deterministic is to build them as lambda functions. So a lambda function is a function that always behaves exactly the same way based on its inputs. Now, an important thing to note is that the source of truth, the golden source of all information, is your event source. It's the input. That input can be made redundant and distributed across the network, but that is your source of truth. It's not a database as your source of truth. It's your event source. It's all the events that came into your system. And as long as that is backed up and reliable, the output of this function will always be the same, always produces the same result. So all you need is the inputs, and you can recreate the system at any point. So say, for example, you've got a bug that only occurs about midday after about 1 million events or so. How do you debug that, right? You can't recreate it any other way. Well, in our case, you just copy the files off production, the files that store all these events, replay them on your development machine, breakpoint it when you get to that event, step through that event, because it's all single-threaded. It's very easy to debug that. But more importantly, once you've fixed the bug, you replay it again, and you can see that you really have fixed that bug, not just a bug or something you thought was a problem. You can see for sure that you've really fixed that problem. So this is a very powerful way of ensuring you produce reliable, dependable code that's easy to fail over, because you always produce the same results. If you've got a second or third system, you will produce the same results again. And like I said, the key point here is that your golden source of information is the queue, the redundant distributed queue, which has all the information that function will run off. Now, the problem with a function is that you can only implement certain logic this way. For example, a matching engine, you could not, or an order manager, needs to have state, because what you do with an order depends on what other orders are in the system. And the way to deal with that is to give the function a cache. And that cache is derived from the queue. So if you delete the cache or you lose the cache, that's not a problem. You can rebuild it from a queue. That takes time. You'd rather not have to do that if you didn't need to. But it's always possible to recreate the state at any moment on another machine, either for testing or for failover purposes, from the inputs. And that state is just a cache. And what you've got there is still a function, always produces the same result. Now, a key thing, which is often difficult for developers to get their head around, is that one of those inputs, one of those things that your program is a function of, is time. Time is also an input. Now, in a lot of code, you're probably used to saying, if I want the time, I'm just going to get system nanotime or local date or system current time millis. The problem with that is that every time you call it, you get a different result, right? If you run it a week later, you will not get the same current time millis. Whereas if it's recorded in your input and you use that, the time that's derived off your input, you will get the same result every time. You'll get the same time every time you run it. You get the same expiries, timeouts, any kind of periodic action is reproduced exactly the same. So one of the conceptual changes is not considering time something you can just grab anywhere, but is in fact another kind of input. These can be chained together. So it's very normal for your core system to be stateful, but because stateful processes are more complex, you want them to be as simple as possible. You want to separate out as much logic out of this stateful core as possible. And so you often have normalizing functions. So externally, you might have a REST gateway, or you might have a fix engine, or you might have WebSockets. However you get data into your system, that's often normalized. And it's often not stateful, because all it has to do is translate messages you got in externally into your internal format. And again, at the end, you have the reverse. The reverse is you take messages that are internal, and then you write them out to the rest of the network. By doing this, you now have a series of components that can be tested completely standalone. And even if you've got a more complicated arrangement, to test this central core logic, it can be tested completely independently of all the others. They don't even need to be running. All you need is those inbound messages and the code for the control system. You don't need any of the other components to be running. You don't need a database to be running. You don't need access to any database or any other service. What the control system does is purely a function of the messages that are in its input, nothing else. And it will produce the same result every time. So you can write very easily data-driven tests which expect a certain result precisely, even with things like timestamps and other information. So one of the problems used to be that disk space was expensive. So persisting absolutely everything wasn't as practical as it is today. But nowadays, you can buy disk very cheaply. This is very high performance enterprise grade disk. And yet for about $1,000, you can get 4 terabytes. That's a lot of space. On a cloud solution, you can get very similar price points. So you've got access to a lot of capacity, and it's actually so using just recording everything in, everything out, probably multiple copies across different machines, isn't such a problem as was in the case. So when a lot of RDBMS databases were created, disk space was incredibly expensive and very precious, and you had to use every kilobyte efficiently. When I started my career, the largest hard drive you could buy was 2 gigabyte hard drive. And half a terabyte, or quarter of a terabyte, filled up an entire rack. And it was extremely expensive. Nowadays, you can get a quarter of a terabyte onto a pen drive. Right? So it's a lot cheaper, a lot more compact, and you really can just store absolutely everything. It's not really the problem it used to be. So each microservice should be designed to be deterministic. So that's one of the key principles, because if you have a deterministic system, you can reliably and confidently make changes to your code. You can, and you'll get the same result every time. So to give an example, we worked on a project a couple of years ago where we were required to add a couple of fields to every event in the system. And we had over 200 tests. Now, going through and fixing all those tests took us 2 hours to recreate all those tests. Today, because that's actually a common problem, we can do that in about 15 minutes to go and fix every test, to add 2 fields to every event in a system. And we can do that because we're using data-driven tests, and we're using a system that produces the same results every time. So let me get down to some examples. So as I mentioned before, time is an input. So if you've got anything kind of expiries or timeouts, that should be driven based on an input, not what the current time is right now, because otherwise you can't produce the same result again later. Again, the state of any microservice can be done by replaying the outputs, which means any redundant system will also come to exactly the same state by just replaying the inputs alone. This makes things like failover, restart, and upgrades a lot simpler. Okay, so let's get down to an example. So this is a unit test. A sample unit test for a cryptocurrency-related exchange, or payment system, actually. So this is the basic structure we use in our unit tests. We have a setup file, which has got data that says, these are the things that are just context, reference information, static information. The first one just creates an account, and as you can see, there's a microsecond timestamp in there, which is something we use generally. And then we perform an operation. And lastly, we have an expected output, which again is an event. Now, this output is literally the method call. So in each case, each of these translates into one method call in Java. So there's a method called opening balance, and it takes 1 DTO. There's a method called top up, and it takes 1 DTO. That makes one call out, and that to a method called on balance, and that takes 1 DTO. And you notice that the timestamp of the output is always the same because it's derived from the input. So that the timestamp always gets the same result every time it's run. Now, where this is particularly useful is solving when tests fail and how do I fix them. So in this example, I broke the code by making it expect a different amount. How quickly can I see that the amount is wrong? Well, because it's a string comparison, in reality, your IDE already has support for this. It can compare one string against another and quickly find both the line where there's a discrepancy and what the value is. Now, as you can imagine, if you've got actually a megabyte of input or output expected, so you've got a very large test, and you want to quickly find in some nested structure what has changed, this can be really valuable in terms of solving that problem very quickly. And in this case, for example, I could just take the actual result. If the actual result was correct, as it is in this case, I can copy the actual result and overwrite the file where there's actual, and now I fixed that test, right? I don't have to think, well, what sort of data structure should I now produce and then code it by hand, right? I don't need to write any code. All I can do is copy paste it. Now we have a mode where actually you can do this just for every test. So you can run the test in a mode where it doesn't check the result, it just overwrites them all. And then when you go to check in the code, you do a comparison. Is this a reasonable change? Is this a reasonable change? And if you're happy with all the changes, you can just check them all in without even having to copy paste them. So that's how you can maintain hundreds of tests and correct them for a major change and still deal with it in a matter of minutes. So let's move on to another example, which is a little bit more complicated. So in this case, this is the static information. I'm creating a Bitcoin currency. I'm giving it some configuration, and I'm specifying a tick size and a minimum order size. And I'm also giving it just a dummy price. So then I create an order against this. So it's just a matter of copying a file, changing some of the values, and now I have a new order object. And then I do another order object, which will match against the first one. And this is the actual output, including the comments. So the comments come out of the code. So this is the result you get. You can see that this trade occurs as a result with comments. And again, this is automatically updated if you just accept the new behavior. So you don't even have to write this yourself. Actually, you get 2 trades for either side. So what does this look like in code? Well, actually, what we've designed, again, because we're trying to be very fast, we keep it as simple as absolutely possible. So this component implements the first interface, and then it accepts the second an object of the second interface as output. That's as complicated as it gets, as simple as it gets, sorry. Because we want the layer between our framework and the component to be as thin as possible. Also makes testing very easy, because to create this component, you just call the constructor. That's it. Now the component is created. There's no auto wiring going on, any kind of magic going on in the background. So we can create lots and lots of tests very quickly and run lots of tests very quickly. So not only does restarting this kind of service take only tens of milliseconds, each test only takes tens of milliseconds. So we can run through thousands of tests in under a minute because starting up these components every time is very quick. So what does the data structure look like? Well, this one is a more complicated example. All of this code, all of the stuff in here is in the open source version, by the way. All of the code that this uses is open source. So the comment here is just the comment that you saw in the output. The long conversion allows us to use longs instead of strings. So if we go back a little bit, you can see that there's a trade ID, which is a string. There's a client order ID, which is a string. We've got a symbol, which is a string. But the problem with strings is that they're objects, and they contain objects. So a string is actually two objects. And every time you create one, that's more garbage. And also, you have to go through lots of objects to see any information. If you want to compare two strings, you have to look at every byte in the array to compare them. However, if you're just using a long, a string encoded as a long, that's inside the existing object. It doesn't take up any more space. There's no redirection. To compare a long with another long is a single machine code instruction. It doesn't get any more efficient than that. So longs are the most efficient way to store them in memory and in binary, but they're quite painful to use unless you've got, as we put in here, a conversion. So you can say that when I either read this in as text or I write it out as text, it's going to convert it into a currency pair or a unique ID or a microsecond timestamp. And by using that conversion, you get the convenience of text, but the performance of a low-level binary format. The trade has a very similar thing, where you have a number of IDs. And because IDs have built-in support for multi-line comparison, it can implicitly show you very quickly when a test doesn't produce the result you want, why it is there's a discrepancy. So we're focused, as a company, our focus initially was on just going as fast as possible. We were really focused on CPU efficiency. But in the last couple of years, about 2 years ago, we shifted really towards also developer efficiency, because developers are actually more expensive than CPUs. So if you can make developers more efficient, and there's a real shortage of skills in the developer environment, then you can make more of a difference to the business than just making the application go faster. So we developed a number of techniques to speed that up. So in the simplest case, you can just copy-paste the result, the expected result, over the file, and that corrects that test, no matter how complicated the test is. You can also regress the whole lot at once, and this is something else that we do. So last year we worked extensively with a tier 1 bank, and we not only supported YAML, but we also supported Fix Engine, and again, they were the ones that had end-to-end 20 microseconds delay. So you can get extremely low consistent latencies with a system like this, but also make it very easy to construct more tests and maintain them.